my name is Elizabeth Howard, and I will be doing my presentation over the spectroscopic analysis of dairy cows on global warming. So first we'll start off with the introduction. So the greenhouse effect. So basically what happens with the greenhouse effect is the sun is emitting solar radiation. So that radiation comes towards Earth. Some radiation is going to be absorbed by Earth, and the surface is going to warm up a little bit. And then some solar radiation is going to be reflected back into space and into the atmosphere. So that infrared radiation can be emitted by Earth's surface, and some of that is going to pass through the atmosphere and go out, and some, however, is going to be absorbed by greenhouse gases and then re-emitted in all directions by the atmosphere. And when that happens, it is going to warm the surface of the Earth, and it is going to warm the lower atmosphere, which causes global warming, which is a really big problem that we are experiencing right now in the world. So the temperature without any greenhouse gases should be negative 18 degrees Celsius, but currently we're actually at 14 degrees Celsius. So according to the Environmental Protection Agency in 2015, these were the biggest greenhouse gas emissions in the United States. So as we can see, carbon dioxide is the biggest with 82%. Behind that we have methane, which has 10% of the emissions. After that we have nitrous oxide at 5%, and then after that is fluorinated gases, which is at 3%. Now the gases are called greenhouse gases because they are trapped in the atmosphere, and then again they can re-emit the solar radiation, which causes a heating effect, which acts just like a greenhouse, which is why they're called the greenhouse gases. So carbon dioxide is one that a lot of people focus on because it has the biggest emission rate of the 82%. And that rate is increasing by 1.9 parts per million per year since 2001. And we have different reasons for all these different numbers. So carbon dioxide is going to come from the burning of fossil fuels. So coal, natural gas, oil, things like that. When you burn them, you are emitting carbon dioxide, which goes into the atmosphere. Now, some of that carbon dioxide is sequestered through the carbon cycle with plants and trees, but obviously there's not enough forest on Earth to take care of that. So that is why we have such a high rate of the carbon dioxide. Next is the methane at 10%. It is contributed from the livestock and agriculture, and that's the one that we're going to talk about mainly today. And then the nitrous oxide and fluorinated gases are coming from the industrial activities. So like I said, we will specifically be talking about methane. And why do we care about methane? So methane has a global warming potential, which is a GWP, that is 25 times greater than carbon dioxide. So yes, it has a smaller percentage of emission in the atmosphere compared to carbon dioxide, but it's significantly worse than carbon dioxide. It is extremely dangerous in the atmosphere if it exceeds a concentration of 5%, which we're not there yet, but we're getting there. The methane, when it is in the atmosphere, lasts for a rate of 9 to 15 years, and that rate is increasing by 7% every year. So this is where the methane is specifically coming from. Again, this is according to the United States Environmental Protection Agency. This is current data from 2017. So the majority comes from natural gas and petroleum at 31%. So that's basically the transportation of fuel and other fossil fuels. Next is the enteric fermentation, which is what we will be talking about today. That's coming from the livestock with 25%, then landfills, manure management, and coal mining. So there are animals that have what are called rumen stomachs. So basically, these animals have 4 different parts to their stomach as opposed to ours, which just has the one compartment. So the 4 different parts that we have are the rumen, the abomasum, the omasum, and the reticulum. So what happens with these animals is they only eat plants, and when they eat the plants, they are allowing to get their nutrients because it ferments in one compartment of their stomach before it is digested in the other part. And when this happens, they produce methane, and that process is called enteric fermentation. So basically, the chemical reaction that you're getting is hydrogen and carbon dioxide, which is making methane. And that is the methane that is providing the 25% of the enteric fermentation. So looking at this graph, we can see that ruminant animals, which are animals that have a rumen stomach, the 4 compartments, contribute a significantly greater amount of greenhouse gases compared to the monogastric animals like mammals, humans, sorry. So for example, cattle, beef cattle, where we get our steaks and beef and hamburgers and things like that from, our dairy cattle, of course, where we get our milk, buffalo, all of those are contributing a very high amount of greenhouse gases because of that enteric fermentation. So the methods for the study. So we'll do a little bit of background specifically regarding the study. So the electromagnetic spectrum. So as we can see, there's a wide range going from radio waves over to gamma rays. And what is distinguishing between this is the length of the wavelength. So we see in the visible spectrum, which is right here, between 780 and 380 nanometers. But for the study that they do, to try to track the methane emissions is with the infrared spectrum, which is going to be right here, which is between 0.3 millimeters and 780 nanometers. So if we look at those wavelengths, as our frequency is getting larger, our energy level is getting larger. So that has a direct relationship. That has an inverse relationship to the wavelength. So as the wavelength is getting shorter, the frequency and the energy is getting greater. So again, we see in the visible spectrum, but we are going to be looking at the infrared spectrum for the spectroscopic analysis. So IR spectroscopy, that is infrared spectroscopy. When energy is applied to a chemical compound, a substance, anything like that, the bonds within the molecule start to move. And this happens, they can vibrate, they can rotate, they stretch, they pull, they zig, they zag. They move in every which direction. And there is an absorption that is marked with that energy level. And so what chemists can do is they can look at the chemical composition from the IR spectroscopy. So this is the IR spectrum for methane. So if you notice, there are 2 significant peaks for methane, which corresponds to the chemical structure of methane. So methane, you have 1 carbon in the middle, surrounded by 4 hydrogens. So there is a strong band at 3,020 reciprocal centimeters, and then one at 1,306 reciprocal centimeters. And that is corresponding to the stretching and bending of the CH bonds that are sp3 hybridized. All right, so there is a relationship between milk fatty acids and methane emissions. And so when cattle or cows or anything with a rumen stomach digest, they create fatty acids. And so what the study is doing is they are going to determine whether IR spectroscopy is actually a good way to look at the milk fatty acids. Gas chromatography was the principal method, but it's not ideal. So what they do is they are looking at IR to see if it has good performance indicators, to see if it's good for analyzing the composition of fatty acids. So the study looked at 267 single-bred cows, and they were looking at untreated and first derivative spectrums, which this has the untreated, the first, and the second derivatives, which is basically a different statistical analysis that we won't go into very much detail about. But again, the purpose of this is to look to see if fatty acids analyzed and CH4 emissions have that relationship. So the results. So it was determined that infrared spectroscopy can be used to estimate methane emissions from milk fatty acids. And it can do it with significant accuracy. So what they determined is first derivative treatments are actually the most accurate. Fatty acids are more accurate than group fatty acids. Saturated fatty acids are more accurate than unsaturated. And it is accurate with monounsaturated fatty acids, but not, I'm sorry, that helps if you're on the right side, but not on the polyunsaturated fatty acids. So what this was doing is it was looking at the correlation between gas chromatography, which they know works, and the IR analysis, and this proved that they were all accurate. So IR can estimate methane emissions from cows with high accuracy. Some problems that they run into for the prediction models is that there are different breeds of cows. There are different stages of lactation within these dairy cows that they were looking at, and the season of the sampling. Also, in order to get a greater library of these prediction models, they need to look at different breeds, different countries, and different seasons. And those are my references. Thank you very much.